This question focuses on understanding how Sklearn's enet_path function organizes its output, specifically the coefficient matrix, which I'll call cofs. I'm given that the design matrix x has 100 samples and 5 features, and the target vector y has 100 values. The cofs matrix, which the function returns, supposedly has dimensions 5 rows and 100 columns. I need to determine the meaning of those rows and columns. I'm given that the design matrix X is 100 samples by 5 features, the target vector Y has 100 values, and the resulting coefficient matrix cofs is 5 rows by 100 columns. This is key information because the dimensions of cofs directly relate to the number of features and the number of regularization parameters, alphas, used in the elastic net regression. This statement is true. Each row in the cofs matrix corresponds to a single feature from the dataset. The values within that row show how the coefficient for that feature changes as the regularization parameter, alpha, changes. I'm essentially seeing the path of each coefficient's value as I adjust the amount of regularization. This is also true. Each column represents a snapshot of all the feature coefficients at a specific value of alpha. As I move across the columns, I'm seeing how the model changes as alpha changes. This is a very crucial concept. I found that this statement is false. The number of columns in cofs is equal to the number of alpha values used, 100 in this case, and that's unrelated to the number of samples in my dataset. The number of samples influences how the coefficients are calculated, but it doesn't determine the number of columns of cofs. This statement is true. The number of rows in cofs 5 directly matches the number of features 5 in the design matrix X. That's because each row represents a feature and its corresponding coefficients at different alpha values. The entire problem revolves around analyzing the output of the elastic net regularization path, which is a method to find the optimal coefficients for a linear regression model by varying the amount of regularization. Enet combines both L1 and L2 regularization. This instruction simply tells me that multiple options could be correct in the quiz. I have to carefully analyze the statements I reviewed above to pick out all the true statements, which were A, B, and D. This is the title of the problem. We're going to analyze the results from an elastic net regression, a type of regression that uses both L1 and L2 regularization to prevent overfitting. Think of it like finding the sweet spot between model simplicity and accuracy. This tells us the shape of the output array from the enet_path function. It has 5 rows and 100 columns. I'll show you what this means for the coefficients below. Each row represents a feature from the dataset, and each column represents a different level of regularization strength. Think of it as a recipe book where every row is a different ingredient and each column is a version of the recipe with a different amount of each ingredient. The recipe book output has 5 ingredients and 100 versions. This row represents the coefficients for the 4th feature, out of 5, in the design matrix. I'm visualizing it as a single row in the cofs matrix, where each cell holds the coefficient value for this specific feature at a particular value of alpha. Similarly, this row displays the coefficients for the 5th feature across all alpha values. Think of it as a horizontal summary of how the model's weight changes for this variable as regularization strength varies. This column shows the coefficients for all features, 5 of them, all calculated using the very first alpha value used in the elastic net path calculation. I see this as a snapshot of the model's parameters at a specific level of regularization. This column represents the model's coefficients, for each of the 5 features, at the second alpha value. It's like taking a photo of the model's parameters at a slightly different level of regularization than alpha 1. This ellipsis indicates that the pattern continues, showing the coefficients for all features at subsequent alpha values, alpha 3, alpha 4, and so on up to alpha 100. It's showing the complete regularization path, with each step showing how the model's weight changes across features. We start with a design matrix X of size 100 rows and 5 columns, representing 100 samples and 5 features. The target vector Y has 100 values, one for each sample. This is the data we'll feed into the elastic net model. I use scikit-learn's _enet_path function. This function is a powerful tool for finding the best regularization parameters for an elastic net model. It does this by calculating how model coefficients change as I adjust the regularization strength. The output _cofs is a 5 by 100 matrix. Each of the 5 rows represents the coefficients for a single feature. Each of the 100 columns shows how those coefficients change with different values of the regularization parameter, alpha. That's a lot of information. We're analyzing how the coefficients in an elastic net regression model change as I vary the regularization strength. Elastic net combines lasso, L1 regularization, and ridge, L2 regularization. Finding this path helps to find the best balance between model complexity and prediction accuracy. I have a multiple choice quiz based on the _cofs matrix from the _enet_path function. I must carefully analyze the dimensions to answer correctly. I see we're working with a design matrix, X, which has 100 samples and 5 features. Think of each row as a different data point, and each column as a different characteristic of that data point. This simply means X is a 2-dimensional array with 100 rows and 5 columns. This is the scikit-learn function I'll use to calculate the regularization path for an elastic net model. Elastic net combines lasso, L1 penalty, and ridge, L2 penalty, regularization to prevent overfitting. In the output matrix, _cofs, each row represents the coefficients of a single feature. Since I have 5 features, I have 5 rows. Each column represents the coefficients for all features at a specific value of the regularization parameter, alpha. Alpha controls the strength of regularization. More alpha means stronger regularization. I have 100 different alpha values and therefore 100 columns. To reiterate, I have 100 different alpha values, resulting in 100 columns of coefficients for all 5 features at each alpha value. I also have a target vector, y, which is a single column containing 100 corresponding values for each data point in X. This function gives me the set of coefficients for different values of the regularization parameter, alpha. The output matrix, cofs, contains these coefficients. The number of rows of the _cofs matrix matches the number of features in my input data, design matrix X. The number of columns in the _cofs matrix represents how many alpha values were used in calculating the regularization path. My input data consists of a design matrix X and a target vector Y. This is standard input for regression models. The output is a matrix with 5 rows, features, and 100 columns, alpha values. This is important because it tells me how to interpret the output. The number of rows in cofs directly corresponds to the number of features in my design matrix X. This is a direct consequence of how enet_path arranges its output. We're analyzing how the elastic net regularization path is represented in the output of the scikit-learn function, _enet_path. Specifically, we'll focus on understanding the structure of the coefficient matrix. This is a great way to deepen our understanding of how regularization affects linear models. I'm given a coefficient matrix, _cofs, with dimensions 5 rows and 100 columns. This matrix comes from the output of _enet_path, a function that calculates the regularization path for an elastic net model. My task is to understand what each row and column represents. The function _enet_path is the star of the show. It calculates the coefficients for an elastic net model across a range of alpha values, the regularization parameter. Each alpha value controls the strength of the regularization. Think of it as a dial. You turn the dial, change alpha, and the coefficients adjust accordingly. I'll explain in more detail how these alpha values create the regularization path. The _cofs matrix stores the results of _enet_path. It is a 5 by 100 matrix. I know that each row represents a feature, and each column represents a different alpha value, strength of regularization. So, the 100 columns represent 100 different alpha values, and the 5 rows represent 5 features. Makes sense, right? I have a design matrix X with 100 samples, rows, and 5 features, columns, and a target vector y with 100 values, samples. These are the inputs to the enet_path function. I want to analyze the coefficient matrix COFs that is generated. This statement is true. Each row of COFs holds the coefficients for a specific feature as we adjust the regularization strength, alpha. For example, the first row represents the coefficients of the first feature over all 100 alpha values. Another true statement. Each column represents the coefficients for all features at a particular alpha value. It's a snapshot of the model's coefficients at a single point in the regularization path. Absolutely correct. The number of rows in COFs 5 matches the number of features in the design matrix X 5. This makes perfect sense because each row represents a feature's coefficients. I'm analyzing how the elastic net regularization path is shown in a matrix. The elastic net combines lasso, L1 penalty, and ridge, L2 penalty, regression techniques to shrink coefficients and prevent overfitting. The path refers to how the coefficients change as the regularization strength, alpha, changes. I'm presented with a problem focused on understanding the structure of the coefficients matrix, COFs, returned by scikit-learn's enet_path function, which calculates the elastic net regularization path. The COFs matrix holds the coefficients for different regularization parameters, alphas. I have the dimensions of the design matrix, X, the target vector, Y, and the COFs matrix. My task is to determine which statements about the structure of COFs are true. I'm given that the design matrix X has 100 samples and 5 features. The target vector Y has 100 samples. The COFs matrix, the output of interest, has 5 rows and 100 columns. This tells me about the dimensions of my data and the output that I need to interpret. This is a crucial piece of information. This tells me the dimensions of the COFs matrix. The 5, 100 notation means there are 5 rows and 100 columns. I will use this to analyze the structure of the coefficients. This is a visual representation of the coefficient matrix. I use it to understand how the rows and columns represent features and alphas. Think of it as a spreadsheet. This diagram confirms my interpretation of the 5, 100 dimensions. 5 rows, features, and 100 columns, alphas. Each cell contains a coefficient value. Each row in COFs represents a feature from the design matrix X. This is the coefficient for the first feature across different alpha values. It's like tracking how important a single ingredient is in a recipe, as you tweak the overall recipe's complexity. This row represents the coefficients for the second feature across all alpha values. Similar to the previous ones, this row shows the coefficients for the third feature, each value corresponding to a different alpha value. The coefficients for the fourth feature are here. The fifth feature's coefficients are shown here. Each column in COFs represents the coefficients for all features at a particular alpha value. This column shows those coefficients for alpha equals 1. This is the coefficient for all features at alpha equals 100. The ellipsis indicates that there are 98 other columns, each representing the coefficients for all features at a different alpha value.